Hi, we are the Chemical Engineering Design Team 7, and we are working with the Spring Valley Student Farm to design an aquaponics system. I'm Henry Mackin.
I'm Caitlin Cushman.
I'm Autumn Wagner.
And I'm Lauren Contenta.
For our project, we were tasked with designing a crustacean-based aquaponics system for UConn's Spring Valley Student Farm. Aquaponics describes a system in which plants and aquatic animals are grown in water. Our design was intended for growing lettuce, tomatoes, and cucumbers, and raising crawfish in one of the farm's greenhouses. Aquaponics systems host a symbiotic environment where the crawfish provide nutrients for plant growth, and the plants clean the water that will return to the crawfish. So why design an aquaponics system? There are many benefits. Aquaponics is a more environmentally friendly way of farming, as water requirements and system waste are reduced. The plants of choice will have longer growing seasons when grown this way, and since these systems do not use soil, they do not need much space to function successfully. They can be built in backyards and do not require a lot of maintenance, which makes them a good alternative method of farming.
The nitrogen cycle is the foundation of the system. Beginning with the ammonia coming directly from crawfish waste, the nitrosomonas bacteria break down the ammonia into nitrite. Nitrite is then converted into nitrates by the nitrobacter bacteria. These nitrates are then taken up by the roots of plants within the system to sustain growth. These aerobic bacteria are the foundation of the system, and the kinetics of these reactions lay the groundwork for the infrastructure of our design.
Our system has three main design requirements that greatly influenced our design process. The first is the physical constraints, as the system is housed in a greenhouse with both limited space and power. This influenced us to use the multi-purpose design of the Dutch buckets and use gravity as much as possible. We also like to design with modularity in mind. All sections of the system can be isolated in the event of disease or contamination, all while still operating and keeping the crawfish and plants alive. We first modeled the flow of water through the system using Aspen Plus and ComSol to size the pumps and ensure a constant cycling of water through the system. We then modeled the reaction kinetics of the key components of the nitrogen cycle that Lauren mentioned before using Aspen Plus and MATLAB. This gave us an idea of how much ammonia the crawfish would be producing, and therefore how much nitrate the plants could uptake to make sure that our system was balanced and sustainable.
Here's the diagram of our final design. It shows how we have set up a modular design to accommodate both coupled and decoupled systems, and a hybrid growing system with Dutch buckets and deep water cultures. We have a 440-gallon tank that will hold 150 crayfish. The water from the tank will be sent to the swirl tank to filter out solid waste. The mechanical filter is used if the system is decoupled. From the swirl tank, water enters pipes to be delivered to 30 Dutch buckets. We intend to grow tomatoes in the Dutch buckets. From the Dutch buckets, it enters the deep water culture, where we will be growing anywhere from 35 to 55 lettuce plants, depending on the rack used. The lettuce and tomatoes from our aquaponics system will be combined with other produce from the farm and provided to UConn Dining Services, where it will be served around campus. Unfortunately, we do not have the system built and running. In the future, we hope that our work contributes to the growing research into aquaponic systems, which will help further environmental and sustainable agriculture.
We would like to acknowledge the hard work and support from Dr. Wagstrom, Dr. Parnas, Julia Cartabiano, and the students of Spring Valley Student Farm. Thank you all for everything, and without your support, we would not have been as successful.